Hey guys, this is Terrence. Welcome to the second part of our waffle surface pattern. If you haven't watched the previous video, please use the link above. Take some time to quickly go over that one. And in today's video, we will use the Python's randomness function to add some complexity to our currently regular looking grid. We will make it looks more dynamic and add thickness to it, thus finishing up the whole pattern. Now, let's get right on it. Before we start coding, let's quickly go through what we have done at the last week's playground. We first created a surface, used the pi value and the math sign function. Then we talk about what is the NURB surface UV domain, how to divide those domains, and how to use the division to subdivide the curved surface. Then at last, we introduced the way to calculate the surface normal on the specific position on the surface. Use the UV value, we can get a normal, and we can scale that normal to move the point away from surface. Thus, we can create the second layer of the grid. We loft these two layers of grid and create a solid object like this. But the problem of this pattern is this one looks still very, very normal, very plain. It's lack of the computational feeling. So in today's video, we will try to add some dynamic features to this pattern. And first, I want to remove these two nodes, which makes our PC super lagging. And I want to visualize this part. Now you can see we have two layers of points, we have two layers of polyline. Now I want to import a random here. Oh, I could actually say from random import random. This function generates a random value ranges from 0.0 to 1.0. And also another function is seed here. Because we are designers, we don't want every time when we are executing the code, we get a completely different result. So we should set a fixed seed here to ensure every time we run the code, we get the same result. I want to set this as rseed here, and add a new input here called rseed as well. Rseed, save it, and try to run the code. Let's see. Oh, sorry. Add a trigger here. Trigger. Connect this to our run it, and we have this input. We match this name with this name, then we can input our seed here. Save it and run the code. Now we can see there's nothing changes here because we haven't used the random value in our function here. We can say we can modify these two parts, these two values. We can modify U position and V position. So first, let me do something crazy to show you how the randomness affects our surface divisions. I can say U position equals to U position plus equals to a random value, and V position plus equals to a random value as well. Save it and run it. Well, the whole thing is now getting very crazy. Let me explain what's going on here. First, let me bring up this sketchbook, and I'd like to draw a rectangle which is a simplified NURB surface. It has the U domain and the V domain, and each domain has a start value and an AND value here. V domain also has a start value and an AND value here. And last time we generated a number sequence start from 0 to 1 with a step 0.1, 0.3, 0.4, etc. When we multiply each of these values to the end of domain, we will get a series of points or a series of numbers on this domain in sequence. Then we can use these divisions, this U division and the V division, to create the point on the surface. Then we just use this point to subdivide the curved surface. And as you guys remember, we also introduced the Bezier curve. In last video, we used the Bezier curve to remap these values to make some part larger but some part narrower, like this, some part narrower, and then we can use the mapped values to adjust the point layout on the surface. I think I can bring up the grasshopper here. Oh, I already did this. These are our mapped value and these are original value, and we can see we just use the Bezier curve to swift each value or slightly away from its original value, and this can change the total layout of our point distribution. But today, when we introduce the random function here, I can say random. Oh, let me make this a little larger. Random function, we actually generate a series of number ranges from 0.0 to 1.0, and they are completely non-sequential. They might be 0.8, 0.41, 0.59, or 0.9. These just examples. But when we add each of this number to our original list or even to our original mapped list, like this, we will break this number sequence, and maybe we will get a set of number like this. We will get 0.2. When we add this with this, we will get 0.9. This will be 0.61 and something like this. At this time, each number becomes very large compared to its original number, compared to its ancestor. And in this condition, this number becomes non-sequential, which makes the point distribution on the surface become non-sequential. And let's think about this. Maybe number 0.2 locates somewhere here, but 0.9 locates somewhere here, 0.61 locates somewhere here, and some number like if we have 0.5 in the original list, but we add it with 0.9, which is randomly generated, we will get a 1.4, which is already out of our domain. And this might be, as we mentioned, this 1, 2, 3, 4, and the point will scatter randomly without any sequence that will cause the distribution, the point distribution completely chaotic like this. And my solution is to limit this randomly generated number within a very narrow range. I set it ranges from 0.02 to 0.002, from negative 0.02 to positive 0.02. And in this condition, no matter what kind of number generated within this range, when the new number adds with the original list, that will not significantly change the sequence of the original list. I mean, I mean, if we do this randomly, let's draw a line. This 0, this 0.1, this is 0.2, this 0.3. When we add this number, with some number generated in this random range, we will got a new number slightly next to the original number without intersecting each other's domain. So I don't know, am I correctly explain this, but let's do it in the code that will be more clear. So here, let me navigate to these two lines of code. Let's first multiply the random value with 0.04, then minus 0.02. And we do the same thing in the v position and minus 0.02. And these two lines of code ensures us to generate a random value that ranges from negative 0.02 to positive 0.02. Let me first save this code and go back to Grasshopper, run it. Now, as you can see, everything just goes back to normal, and the point just slightly move away from its original point or original position. The next thing I want to do is I want to keep these edge points unchanged. I don't want edge point move around. I just want them stick on where they were. And to do this, I just need to add an if condition. If u position not equals to 0 and u position not equals to 1 with a column, then add indentation here, save the code, run it. We just make sure all the points locates on the start of u domain and locates in the end of u domain unchanged. And then we can expand this by doing the same thing on the v position not equals to 0 means when the v position not at the start, not locate on the start of the domain, and the v position not equals to 1. Save the code, run it. Now we put all the edge points back to their own position. We don't allow them to move around. And the next step is, as you guys can see, the distance between the two layers of points are identical, which is not dynamic at all. And what I want to do is to change the amplitude of the normal value a little bit to make some points move further away its original point, but some point moves closer to the original surface. To achieve this, I should go to this function, the normal point, and in the amplitude part, I will let me multiply the amplitude with a value random multiplied by 0.5, and I think this generates a value ranges from 0 to 0.5. Let's save it and check the result. Now it becomes a little bit narrower, these 2 points, just like these 2 points. And I think I can just add these numbers by 1. Okay, now the space becomes much more generous. This means we generate a random number ranges from 0 to 0.5. But after adding this random number with 1, this ensures us generate a value ranges from 1 to 1.5. And now we have our base curves, base polylines. The next step is to generate some solid objects based on these 2 layers of polyline. Now let me just bake these polylines out. I think this will be more straightforward. As what we did last time, we just loved these two layers of polyline and created a geometry like this. And today's mission is to make this shape has thickness, and a routine or a commonly seen solution I can think about is to offset the polyline here and offset the polyline here. Then I can loft these two layers of polylines. But the problem is here, now you can see a very weird thing happens on the corner of the polyline. That's because the 4 points on this polyline are not coplanar. Not coplanar means they are not on the same plane. And in this condition, if we offset this curve, we offset this polyline, we will definitely result in some weird outputs like this. So to address this, my solution is, instead of offset curve, I can try to scale. This polyline. I can say we should find its center and do something like this. Then we do the same thing on the first layer of polyline, center and scale. Scale. This one. Oh, we don't have this. Scale it. Center. Here and here. Then we can loft these two newly created polylines. Then we just we can keep lofting these two polylines and these two polylines to create a solid surface, like what we did on the matrix wall. We did the same thing on that example. Now let's do this in our code, but before doing so, I'd like to separate these two layers of polylines. I want to first create the upper layer, no, the lower layer of polyline by using polys a equals to a least comprehension polys I for I in range length polys if I modulo by 2 equals to 0, polys b equals to polys I for I in range length polys if I modulo by 2 equals to 1. So the polys A could be our first layer of polyline, and polys B could be our second layer of the polyline. And let's run the code, no errors, and let's add 2 more outputs to check did we successfully divided these 2 layers of polylines. Let's do it by modifying this name as polys A. Check it. Oh, run it. And copy this. Polys B as another output. Run the code again. As you can see, now we successfully divided these 2 layers of polylines. Now we can just loop over the first layer of polyline. We can say for I in range polys A length polys A, like this. And inside here, we will try to process these polylines unit by unit. And the first step is we should find each polyline center point. And here we need to add another function called polyline center, or we can just directly scale the polyline inside this function. So we can say scale poly. We will have two inputs, the polyline itself and the scale value. Let's go back to our polyline, and this time to calculate the center point of this polyline, we can't use the curve area centroid function because these 4 points are not coplanar as we just mentioned. We will use another method called average centroid, and let's do it. So first we need to extract the points on the polyline. We should say points equals to rs curve edit points to extract all the points on the polyline with the input polyline. But this function actually outputs 5 points instead of 4 because the end point and the start point are at the same location. This curve is closed. So we need to add some more code to avoid selecting the last points. And then we just calculate we just put all the points x value into the list, put all the points y coordinates into a list, and put all the points z coordinates into another list. Let's do this. Like pts x equals to a list comprehension pt0 for point in points, and copy this 3 times. We modify this as pt's points y means all the points y coordinates and all points z coordinates. Modify this index, and then we still need the number of points, which is pt number equals to length points, and then we just calculate the average center here equals to a tuple. The first value is the sum of the ptsx divided by the point number. We copy this and paste. This should be y and this should be z. Save it. After we have this center point, we can start to scale our object. Now we can say out polyline equals to rs dot scale object, which requires 4 inputs. The first one is our polyline. The second one is our average center. The third one is a scale, but the scale should be in the format of tuple. So we need to type it in this way. And the last input is true because we don't want to transform this original curve or original polyline. We want to make a copy of this polyline, then transform it and save it. Then return this. Oops, sorry. We're here. Then at last return this out polyline. Poly. Yes, save this and use this function in our loop we just created. We can say new surface equals to an empty list. And now let's offset the first layer of polyline. Let's say poly AO equals to scale poly, the function, and polys a with an index I. The scale value we set it as 0.9. We do the same thing on the poly bo and polys b. Save it. Let's see, did we successfully generated these new polylines, and we can create new variables here called polys AO means polys A offsetted equals to an empty list, and we need to have a polys BO as an empty list as well. Then we just append the newly created polyline into the list. Polys AO dot append poly AO and polys BO dot append poly BO. And let's see, here we can just modify these two outputs, polys AO and AO and polys BO. Save the code here and run the code here. As you can see, we already have these newly created polylines. The last step, just hard coding to loft all the polylines to make it a solid object. Now we can do new surface. Oh, sorry. I think we should add a new variable here. No, we already have this new surface here, so we don't need to worry about that. Plus equals rs.add loft surface. We are familiar with this function. Polys b with an index I and polys bo. Yes, polys bi. Yes, this is the locates on the second layer, and the next one is locates on the first layer. We should say AO. The third one is A index I and polys B with index I. The last one is poly AO and poly BO, two newly created polylines. Then out. Okay. We add the last output here. Out surfaces equals to an empty list. Then join all these four newly created surfaces together. Use the rs dot join surfaces and with the input new surfaces, and append this new join. Sorry, here should be join surfaces, and append this newly created object to the out surfaces. As rfs append this one. Save it, and apparently this is a wrong spelling. Save it and run it. There's an error here. Let's check which line of code goes wrong. 102 add loft surface. Oh, okay, I know what's wrong with these lines of code. I should remove this. This has still spelling issues. Run it. Okay, I think it works. And last step, we just add our final output here. Out surface surfaces, and no, this should be a geometry. Run the code, and as you guys can see, we have what we want here. And I save it and just decrease the amplitude a little bit. And if we change our seed to 30, we will have a different layout or different shape of the waffle grids. And that's it for today's video. Thank you so much for watching. I already put the code and the GH file into my GitHub repository. You can find the link in the description in the description of this video. And if you guys have any comments, thoughts, critics, or if you guys have any kind of pattern want to see how I create it, please let me know in any ways you want. And for the next topic, for the next week's topic will be something like this. I want to use the Bezier curve to create a kind of geometry that we haven't touched so far. So see you next week. Bye bye.